Hello, everyone. Welcome to my talk. This is a pre-recorded version of my talk, which I thought I should do in case of technical problems. If you see this, then this was probably a good idea. Let me share the screen with you. So, I want to talk today. I want to talk about joint work with my colleagues Emily Rivett-Carnac and Jane Morgan. Because I think it's on one hand very disappointing that we all can't meet in person, it's also quite lovely that we can speak to each other over quite long distances, and I can present my research to you. Just to make the point a little bit clearer, this roughly is where many of you are or would be. And here in Johannesburg, South Africa, this is where I'm sitting at the moment and recording this. Okay. So what is my talk about? It's on the metric dimension. So let me go right into things. Let's say we have the problem that in a building which we model by a graph G, we want to install smoke detectors. All smoke detectors can detect the distance to a possible fire, but they're not able to detect the direction to this the direction in which this fire is. And what we want to do is we want to place smoke detectors so that we can detect the location of a possible fire. So let's rephrase that, because we model our building by a graph. We can think of this as having a graph, and we want to place our smoke detectors in the vertices of our graph so that we can determine the possible location of a fire that would be in a vertex. Possibly a vertex in which we have a smoke detector, possibly another vertex. Okay, let me give you the definition we need for that. Assume that G is a connected graph, a set of vertices, and this is going to be the places for our smoke detectors. The set S of vertices of G is a resolving set if no two vertices of G have the same distance to all vertices in S. So in other words, there is no vertex in the whole graph that to each vertex in S, there are no two vertices in the whole graph that to each vertex of S have the same distance. Okay, let's make that a little clearer, perhaps with a toy example here. So I've got a graph here with 5 vertices, and I'm going to place my smoke detectors in the 2 vertices labeled V1 and V2, indicated blue. And I'm going to show that this is a resolving set. Next to each vertex, I have written 2 numbers. The first number is the distance of this vertex to V1. The second number is the distance of this vertex to V2. So for example, here, the top left vertex is labeled 1, 3, meaning the distance of this vertex to V1 is 1. The distance of this vertex to V2 is 1, 2, 3. And for example, vertex V1, I've labeled 0, 2, because the distance of this vertex to V1 is 0. It's the vertex V1 itself. And the distance to V2 is 2. Okay, and if you now check my labels with the distances, you will realize that no 2 vertices in the whole graph have exactly the same pair of labels, or the same labels. 0, 2, 1, 3, 1, 1, 2, 2, 2, 0. There's no repeat. So that means if I have any vertex in my graph, if I know just the distances from this vertex to V1 and to V2, then I can identify my vertex immediately and uniquely. So for example, there's only one vertex whose distances to V1 and V2 are both 2, 2, 2, and that's this top right vertex here. Okay, so a resolving set is one that does exactly that a resolving set has the property that every vertex in the whole graph is or can be determined if we just know just the distances from this unknown vertex to all the vertices in our set. Okay, now let me use this example of the smoke detectors one more time. We, as so often, we want to use as few smoke detectors as possible. And that means I'm now interested in resolving sets that have minimum cardinality. Okay. And the cardinality, the smallest possible cardinality of a resolving set in a graph is called the metric dimension of our graph. And usually I denote the metric dimension of G by K of G or just by K. Okay. So now let's compare, or let's relate the metric dimension to the diameter of the graph. Both are distance-based invariants, so it makes sense to relate them, and that's the topic of my talk anyway. So let's say S is a resolving set in our graph G, and the vertices in S are V1, V2 up to Vk. Then each vertex in the graph can be described by a distance vector, and this vector is just the k-tuple in which I write the distances to V1, to V2, to V3, up to Vk. So a k-tuple of numbers, and this k-tuple determines my number uniquely, my vertex uniquely. So that means no two vertices in my graph have the same distance vector, have the same k-tuple. And this idea of the distance vector helps me to immediately find an upper bound on the number of vertices I can have in a graph if I know its metric dimension and its diameter. Let's quickly count that, how many vertices we can have at most, or let's rather get a bound. Okay, well, the resolving set S itself has exactly k vertices. Okay, that's number one here. Number two, how many vertices are there at most that are not in our resolving set? Well, in every vertex that's not in our set is uniquely identified by its distance vector. Now, the distance vector has k entries, and each of these k entries is a number between 1 and k. It can't be 0 because I look at the vertices that are not in the set. Okay, so for each of the k entries of my distance vector of a vertex, I have big D choices if big D is my diameter. And because there are at most big D to the k such possible distance vectors, that means I have at most D to the k vertices that are not in S. So add these two things together, and we get an upper bound on the order of a graph whose diameter is D and the metric dimension is k. And this upper bound is k plus D to the k. Okay, now this bound looks pretty rough and it is not sharp except for D equals 1 and 2. But already the people who found this bound, Chartrand, Poisson, and Zhang, and also independently Kuller, Raghav-Sharari, and Rosenfield, they observed that this bound is not sharp if D is greater than 2. So I want to look at sharpening this bound. Where that happened, this bound was made sharp already by the Spanish group about 10 years ago. And they proved the exact maximum value of a graph of given diameter and metric dimension. And that's this term here of the floor of 2d over 3 plus 1 to the power k plus the sum plus k times the sum over I equals 1 to d over 3 over 2i minus 1 to the k minus 1. Now, that's not a very handy sum. If we approximate it very roughly, then we get that this bound is very roughly 2 times 2/3 d to the k. So nothing like d to the k, what we had a moment ago as the dominating term, but more like 2/3 d to the k. And the graphs they constructed to show that this bound is sharp, well, they're pretty hard to draw unless you do it for metric dimension k equals 2. Then you get something like a big grid of about value 2/3 the diameter times 2/3 the diameter. And to these grids, you attach these triangular bits here that look a little bit like cones that you attach to it. But if you want to do the same or construct the graph for, let's say, k equals 3, then your the square grid that I drew here would more look like a cube grid. And I would attach also then in that case 3 cones, one at the bottom, one at the side, and one in front. Okay, so that's an old result, and it's very beautiful. And it raises one natural question. This question is, can this bound be improved for some graph classes? And one very natural question is, can you improve this bound for trees? Because if you look at the graph, at the extremal graph, it's very far from being a tree. So it's natural to ask, can we improve this result if we just restrict ourselves to trees? And that was our starting point of a very nice joint venture with a French group. And we obtained the result that if we have a tree of diameter big D and metric dimension k, then the order is at most this value here, which is very roughly 1/8 times k times d squared. Slightly different for the diameter being odd or even. But I thought I quickly show the unique extremal tree. I've done that only for even diameter, in this case diameter 6, and that's what we called a hairy spider. This is the graph, the tree for metric dimension k equals 2. It has one more leg, k plus 1 legs, so 3 legs, and all but one leg is hairy. That means if I place my resolving vertex here at the end of the legs, then each bit of the leg has a hair that reaches to the bottom as far away from the root here as the vertex in my resolving set is. Only one leg has no hairs. And this graph is the unique extremal tree. It looks somewhat similar if the diameter is odd. Then you take roughly 2 copies of this tree and join them together. Very roughly. There are a few degrees of freedom that you have, but that's roughly what it is. Okay. Now we try to generalize this result a little bit in our research that started with this bound for trees. And we looked at tree width, and we found that if we have a graph that has a tree decomposition of width W and length L, then and diameter D, then the maximum, or then the order is bounded from above by k times d squared times 2L plus 1 to the power 3W plus 1. And well, the order of that. This bound is certainly not sharp, but we think it's a pretty good start. And it shows that in this case, the order of the graph can't be exponential like d to the k, but it will be polynomial in d and k. Okay, and for specific graph classes with the same group of people, when looking at outer planar graphs, we showed that we can have approximately some constant times d times k square vertices at most. However, we are not sure what exactly the value of the coefficient of d times k square is. So there is still a little bit of work to do. And some members of the group with which we found these results, Foucault, Metzius, Nazarazzer, Parot, and Valikov, before this collaboration, proved by looking at interval graphs and also permutation graphs that also for these graphs, the order is bounded by some constant times dk squared. And they proved that even further for unit interval graphs. And this bound is best possible too, except again, it's not clear what exactly the coefficient, the best possible coefficient of dk squared should be. Okay, and for planar graphs, we are not quite sure. We were not able to do that, so that's another open question. Okay, so what's the new main result that I want to present today? We also looked at a pretty large class of graphs, bipartite graphs. And we found that for bipartite graphs, this original bound by the Spanish group that was approximately 2 times 2/3 d to the k can be improved to, well, I've written the long precise value here, but it's, if you approximate that a little bit, you find that this is about 2 times d/3 to the power k. So where the Spanish group for general graphs had 2/3 to the power 2/3 d to the k, we have only d to the d/3 to the k. So that's an improvement of a factor of about 2 to the k. And our graphs, or extremal graphs, that they look pretty much like the extremal graphs we have seen, except we have to make our graph bipartite, and then we can't fit as many graphs in our rectangle, as many vertices in our rectangular grid as they could. Okay, and the last result that I want to mention is that also when looking at bipartite graphs, that we were also able to improve a bound, a lower bound on the metric dimension by Gary Chartrand, Poisson, and Zhang in terms of maximum degree. And they proved that if we have a graph of maximum degree delta, then the metric dimension is at least the log to the base 3 of big delta plus 1. Big delta is the maximum degree. And we managed to show that if our graph is bipartite, then this can be improved to log 2 of delta. And that's an improvement by a factor of about 1.59. And both bounds are sharp. I've given one example, but I don't have the time to explain that here. So my time is up. Let me thank you. And rather than the thank you slide, I thought I share with you the view or a view from one of our game reserves, Pilansberg, about 2 hours drive from Johannesburg, which, if you are in Johannesburg, you may want to visit. A lovely place. I thank you for your attention and keep well.